Yeah, now it is going. But this is not working yet. This is on. On here off. Okay. Okay.
Okay, so let us start. Fine. So the title of the talk is Time Travel Through Wormhole. Fine. So
Tap here. Okay. Big online.
yeah. So, coming to the title of the talk, the time travel through the wormhole. So is it that is a hard question. Can you travel through wormhole? Sure. But it's pretty much possible. Huh? Oh, right. So I'm going to explain it. Then we'll come to the things. Fine. So from time I thought it possible. Right. So how do we okay. So moving contact. Fine. So in moving contact, Jodie Foster traveled to another planet by the help of wormhole. Now coming to the next one. Or okay. Now coming to Interstellar. Most of you guys have watched it. Now if you go for these three movies, what did you say? Time travel is possible. But you guys don't know. All picture. Okay. Science fiction part. Then we come back to science. Okay. Then coming to the end again. Right? Okay. So this is concept of this time machine. So we will go back to time. Fine. Right. Now, wait, series. Because once the computer started, all the data can flow. Then now also most of the people are habituated with the web series. So all of us addicted on the web series due to COVID. Right. So coming to the web series. Right. So here also we want to connect the present, past, and the future. So that's what I mentioned here. So if you go to the Hollywood depiction, right? So the interstellar travel continues to fascinate the scientists, right? So these are exactly the wormhole, but how do they work? So if you look at these Hollywood movies or the Avenger Endgame or the Dark Web series, so this science fiction says that the time travel is possible through wormhole, right? Then the question is, what is behind it? The work. Okay, right. So basically, the wormhole is a shortcut path. Fine. So it is a shortcut between two distinct regions in the space time. Right. So okay. So paper and sheet of paper. It's where so someone they right? So point then we just right? So now go back one. Then the thing is done again. So here that's what we do. So go to embedded diagram. So go to so tube like structure. Basically, make a hole and put it in. Then A to B, so that is the shortest distance to be over point A to point B. Okay. So if you go right? So yes. So you entered in 3D. Right? Then you have 2 points. The points A and B. Okay. So if you go for 2D, surface length is the. So when you hold it, then you get the tube-like structure. So that is what the surface distance. Okay. So hold it, go for you want to travel from Moscow to New, right? So if you go for you go for the wall map and go for the globe. Yeah. That is what if you go for Riemann geometry. I'm not talking about Riemann geometry now. Okay. Because distance is geodesy. So I'm not going to the Euclidean geometry. Right? Just go for Euclidean geometry. Don't talk about geometry now. Right. So if you go for one hanging map. So this is the one. Right? Then we must go to newer. So I will the distance. But all of you must travel to the flight. So when you are flying, what is happening? So then you are the flight, right? When you go for the flight, you start going here. So must go to Newark. You are now it is in between these two, which is the second. So if you want to read, so if you want to the wall hanging map, then there is the distance for the globe. Okay. If you go for the globe, this is the distance. So if you say that, so you will go for a chord space, right? So this is the surface distance. Then you can talk about the Euclidean geometry, it is the straight line. Then when you go for Riemann geometry, it is the geodesic. Mathematics will come to the picture, right? Okay. So basically, this is the idea that I want to say that if you go for the folded piece of paper, so when the 2D is embedded in 3D, how will you get the surface distance? Right. Okay. So basically, this one is a three-dimensional workbook with another entrance and exit. Okay. So what you have to enter one side and exit other side. So it has an entrance and exit, and then years. If you go for not like the tube-like structure. Okay. So not like the two-dimensional ring like mouth and the paper tube. Right. So there are these spheres in both the ends. So that is what the entrance and exit. And if you go for the particular friendly wormholes, this is expressed in the embedding diagram. Okay. And most popular are the Schwarzschild embedding diagram. Okay. And all of them Schwarzschild block volumetric because you guys astronomy, right? So let us leave about it. So starting with Schwarzschild black hole metric, then we go for the black hole and wormhole. I will come later. Right. So basically, this is the iconic diagram of the wormhole. Right. So this is known as the M. So this is the throat which connects two mouths. This side is one mouth, other side is another mouth. So this is the entrance and exit of the wormhole, and you have to travel through the throat. Right? So entrance two sides. So these are the spherical regions. So that is what the iconic diagram of the wormhole. Fine. So now coming to the general relativity. So once you come to the general relativity, basically they are filled. So we are expected that they are filled with exotic matter. That is the matter does not satisfy the energy conditions. So coming to the Einstein's general relativity, if you go for the Rayleigh equation, Rayleigh equation, then the Rayleigh equations are used to classify geometry, space like, time like, and light like. Okay. So whether the chords are time like chords, space like chords, or the light like chords. Okay. So now we have the energy conditions. Most popular energy conditions are there. So I explain the four most popular energy conditions. Out of that, one energy condition need to follow. Right. So then that is the exotic matter. So if there is an exotic matter in the universe, which indicates that there is a presence of the wormhole. And that is completely theoretical as we started. Right. So it is known as the Einstein bridge, right? It is a topological feature that is fundamental to separate points in the space-time. Okay, so as I mentioned in the iconic diagram, so it has two mouths and the mouth are connected by the throat. Fine. Now coming to the history, so this was wormhole. This name was coined by the American theoretical physicist John Wheeler in 1957, and this is the idea how we get the name as wormhole. So when you look at this picture, so right, so in the account, one has to travel from one end to other end. Okay, so what that worm will do? So in place of traveling on the surface of the apple, so simply we can hold and exit in the other end, right? So the distance for the worm to travel one end to other end of the apple. So that is what the idea how John Wheeler gave this name as wormhole, right? So because if the worm surface of the apple, it is more distance for him, right? So that is what then the idea is mouth, other side is another mouth, then connecting with two mouth of the throat, which is the shortcut distance. Right. Now coming to these two pictures. If you go for the left hand side, just take your fine. So if you take the handkerchief and put some weight. Now this but if you take keep at home, big here. So like what is the result? Simply is a mark, right? So if you go for right? So that is not so if you go to this in the fabric or in your handkerchief, you give some weight, then you can tag towards the center because the gravitational mass, right? If you go for high mass, then you get a tear. That is what your black hole, because the black holes are highly massive. Fine. So supermassive black holes are cause a tear. Fine. So that and it may form a wormhole. So that is what the idea is. Fine. Then these two regions will meet and they will form a wormhole connection. Okay. Now coming to the wormholes. So don't wormholes with the black hole because wormholes are not same as black holes. In simple mathematics, if you go for wormholes, there is entrance and exit. But if you go for black holes, this is the one-way trip. So anything can enter, nothing can exit like light also. Okay. So anything went inside, there is no way to come outside. So that's why we used to say that even if light cannot escape from the black holes. Okay. But wormholes are the two-way trip. One can come Hyderabad and return to Aligarh. Right. But like एक बार ऊपर गया, that is what the black hole. One-way trip. There is no second way. Right. Now coming to the question whether the wormholes exist. So do the wormholes exist? Right? Not naturally. See, that story I will come till 2015. Till 2015, once the event horizon telescope captured the image of black hole, then we are going from the image and telling black hole. Before the same thing, Baba. So before 2019, April 10, black holes are also mystery, right? They are the mystery from everybody. That and India black hole. So in 2019, April 10, once Event Horizon Telescope captured the images, then it is able to use the image of the black hole, the event horizon, and all these things. The same thing till history, and this is a theory. We will come to the picture. Right. So here is the observational evidence like the black holes till 2019 April 10. Okay. But there are solutions like the black holes. So both mathematical solutions have wormholes which started from 1934. Okay. And wormholes completely normal vector with positive energy density. Fine. What is the interesting part? But we like one of the present so travels to the wormhole may unstable. Right. So what we need? We need a stable traversible wormhole. Okay, because we have to travel. And this stable traversible wormholes was given by in 1988. Okay. So in 1988, the paper they published about the traversable wormholes. And if you go for the latest movie Interstellar, you can see Kip Thorne's idea was used completely there. Right. So now coming to the history. So Einstein's general theory of relativity is 1915 November. The article came. Then the five-volt solution given by the Lam in 1916. Okay. Then coming to the Schwarzschild solution. Okay. In 1916, the first exact solution to the Einstein field equations, and using the spherical solution. Right. So this is basically the iconic diagram. Then coming to 1921, the well geometry. And the starting point is the wormhole is Einstein-Rosen bridge in 1935. Okay, so this is the first mathematical proof of the wormhole, and this is the cover page of the book. A mathematical wormhole is a theoretical passage through space-time. Right. Now the story is so then 1935 Einstein-Rosen bridge. Then Gödel gave the time tunnel is possible. So it is in 1948. Peter gave the name as wormhole because initially it was the Einstein-Rosen bridge. Okay. Then 1957 it is wormhole. And as I mentioned, the most promising one is the Morris and Thorne wormholes, which is the stable traversable wormholes in 1980. So this is the most promising one. Most of the research are there in the Morris Thorne wormholes. Fine. Now coming to the types of the wormholes. Basically, the type of the wormholes, it is like the names. Okay. The scientist or the physicist who developed the wormholes, it is by their name. Is Schwarzschild wormhole, Lorentz wormhole, Maurice Thorne, Ellis, then Matt Visser wormhole. So it is the ideas the scientist gave. So based upon the ideas of the scientist, the names are given by the scientist name. Then the based upon their properties. Okay, based upon their properties and behavior, you can go for different type of wormhole. But primarily, there are six different type of wormholes. So what are they? They are traversal. So in traversal wormhole, this is the most familiar in the science fiction. Right? So wormholes are we can pass through from one point to the other point in the universe. Then coming to non-travel, nothing can pass. And the one-way. Okay, so the one-way wormholes are one-way trip wormholes that are the black holes. Now coming to the white holes. Then when we come to black holes, then but there is no existence of white holes. The reason is they are so less massive. They diffuses very fast. Okay, so there is no white holes at all. Right. Then coming to the wormhole, there are two. That means what as I mentioned, you have a round trip. You can go Aligarh and come back to Hyderabad. Okay. Then there are intra-universe, which are located in our own universe, and they are traveling from one point to other point in our universe. Then you can go to inter-universe. So in inter-universe, you can travel from one universe to another parallel universe. Okay, so this is the iconic image from the NASA. Fine. So this is basically the test wormhole. Now coming to the basic idea of the wormhole. So what we will do? We will create a traversable stable wormhole. So we will require for the space travel. Fine. So the idea we go to two-way traversable wormholes. Okay. Right. Einstein is traveling through the wormhole from Earth to Andromeda galaxy. Yeah. Yeah. Yes. That I am coming to mathematics. So this is basically I started with the science fiction. Now I am coming. Now I am in the history of the wormhole. Okay. Then I will come to the mathematical part. Then we will come to the physics also. Okay. So this is basically the history. So what is the basic ideas of the wormhole and the types of wormholes? Okay. Then so now we go to the mathematical model of the wormhole geometry. So coming to mathematics, we need this in here particularly. So if you go for Einstein's theory of relativity, your field equation, the left hand side is the geometry of the universe and the right hand side is the matter content. Fine. Static spherical symmetric metric. Then we need to have a source. Then to connect metric and vector, we need a framework. Okay. So these are the three basic things which we need going for the Einstein's field equation. Fine. So let us start the first static spherical symmetric metric in the spatial coordinates. So your time coordinate and r theta phi are the spherical coordinates. Yes. You can do, so what I will do, I will go for a toy. Right. You can do it. So what I am going to form here, I will toy model with general theory of relativity. Right. Then I will explain what about the matter part. Then I will go for the present research part we are doing. Fine. So let us start at toy model. So I started with a spatial static spherical symmetric metric in the spatial code. Right. Then here if you go, there are two unknowns phi and v. Because your r theta phi are the spherical coordinates, t is the time coordinate. Now coming to these two unknowns. So phi of r and v of r. So phi is the redshift function. Confused with the z, because when you are talking about redshift, then immediately you are going t and z coordinate. So don't go for that. So this is the redshift function and this is the shape function. Fine. So in this metric, this shape function, because this shape needs, because you want to open the throat. If the throat is open, then one can travel. Right. So that's what depend upon the shape function. And the redshift function will be finite here. For getting a traversable, we need this redshift function must be finite. And coming to the radial coordinate, fine. In general, the radial coordinate is from 0 to infinity. Okay, but in this case, it is from r0 to infinity. Well, throat radius. Because our basic idea is the throat has to open. Fine. So your radial coordinate will start from the throat radius goes up to infinity. Okay, so now we minimum conditions when you go for modeling a wormhole. The first condition is known as the throat condition. So the throat condition says that at the throat radius, okay, r is equal to r0, the shape function must be equal. So b of r0 is equal to r0. So this is known as the throat condition. Then the second condition is known as the flaring out condition. It is like a trumpet-like structure. You must have a flaring out condition. That means it is a trumpet-like so that you can exit towards the mouth. So for the flare, the first derivative of this function at the point r0 must be less than 1. It is basically dp by dr at the point r0 less than 1. And the third condition is the asymptotically flatness condition. Okay. The asymptotically flatness condition, the ratio between the shape function and the radial coordinate tends to 0 when your r tends to infinity. So these are the three minimum conditions imposed on the shape function. The throat condition, flaring out condition, and asymptotically flatness condition. Condition, as I mentioned, the redshift function must be finite. Okay, because we need a stable traversable wormholes because there is no horizon. Okay, so in the absence of horizon, yes. Okay, so because yeah, it is the because it shows open step. So when we start infinity, then this step has infinity. So that you get so that it goes out Which one? The B. Yeah, that is what I told. B is the shape function. Shape of the throat actually. Okay. It is the shape of the throat. That I am coming later. That I am coming. Okay, that is the what the exotic method. Like what we used to tell, you go for present pattern of the universe. You have only 5% of the baronic matter and 95% are dark. The dark energy and dark matter. Again, you go for 72, 73 or 22, 23. Depends upon because people told that 72, 20, 73, 22. Anyway, so it is 95 the dark part and 5 is the baronic matter. So that's why I mentioned that don't confuse this exotic matter with the dark matter or the antimatter, right? Because the exotic matter is something else. So that is a mathematical equation I am coming after that. If that violates, then the exotic matter is present. Fine. So here the non-energy conditions that I started that part, the Raychaudhuri equations. Okay, that I am coming. So here I wrote the Raychaudhuri equations. So we have 4 energy. There are 10 energy conditions. Out of 10, 4 are most popular. So the first one is non-energy condition, then the weak energy condition, and condition on the dominant energy condition. Fine. So coming to the energy condition, so they are the Raychaudhuri equations. Fine. They tell the kind of like curves. Okay. So if you go for general theory of relativity, fine, then the non-energy condition. This is the minimum requirement which is obtained strong energy and weak energy. That is, if you go for the, suppose you take the perfect fluid is the matter. The matter content of the universe is perfect fluid. Then you have a pressure and density. Right? So the non-energy condition says the sum of the density plus pressure must be positive. Okay? And since we are going for anisotropy here, so you have the radial pressure and transverse pressure or the tangential pressure. Right? So the density plus the radial pressure and the density plus the tangential pressure, they must be positive. So that is what the null energy condition. So if this violates, suppose the null energy condition fails, the null energy condition fails indicates that there is a exotic matter in the universe. Due to the presence of energy, exotic matter, the null energy condition fails. So violation of this rho plus pi, if rho plus pi is less than 0, then we say that there is a exotic matter in the universe. Fine? Yes. It is exotic. Basically, which are right? Huh? No, it is 5%. We cannot go for the dark part. We don't know the dark part. We'll go with the 5%. Yes. It's on part. See, what the matter is right? So, right? If you want to pressure density, what this condition says, if you have the pressure density less than zero. Because it is going to come because you have to go for negative pressure. When you are talking about negative pressure, you talk about the dark energy. Right? So out of the 95, negative pressure becomes the dark energy. So when pressure is so negative, so then it will density. Right? So if you density, then go for expansion. Because there is part of the strong energy condition. There was the acceleration of the universe, which proved in 1998 and 99. These recent parental articles, right? Before that, there is an article in 1998 that the violation of strong energy condition. If the strong energy condition violates, then the universe is accelerated. Okay. Then you go on strong energy condition, then you tell the rho plus 2pt. Right? The density plus radial pressure and tangential pressure in theta and phi. Because it is all So if this is negative, if this violet, then the universe is active. Okay. So in a similar way, if these two fail, then there is a matter because the failure of null energy condition. And the failure of null energy condition is due to the exotic matter. Due to the dark energy. It is a similar. We don't know dark energy till today also. But we are telling you the negative pressure is due to the dark energy. So in a similar way, if the density plus the pressure is zero, then that is due to the presence of the exotic matter in the universe. Okay, and last energy condition is the dominant energy condition. Density always dominates the pressure. Right? Okay. So after these four energy conditions, we will deal with the first one. For wormhole, we will deal with the null energy condition. Because the violation of the null energy condition is the presence of exotic matter. Right. Now coming to the toy model. So we started with the static spherical symmetric metric, then go for the calculations of the Einstein tensor, and consider the matter content of the universe is perfect. And pi and basically, so G is the gravitational constant. Right? Now as I mentioned, so that I will tell how to calculate. So going for this, we will get the instant field equations are 10, 11, and 12. So these are the three instant field equations. Okay, in general. Then here you have left hand side P unknown and right hand side unknown B. So you have four unknowns with three differential equations. You have three ordinary differential equation with four unknowns. Fine. So how to get an exact solution? Can you get an exact solution? Yeah. So you need another condition, right? That is what the famous we use the equation of state parameter. You go for physics, we are familiar with the equation of state parameter, where we used to say that P is a function of rho. So P is equal to omega rho, right? So that is one way you have to take the pressure and density, then reduce one unknown and go for the solution. And in other ways, what is the other way? One way is considering the equation of state. Then what is the other way? So anybody here mathematics student or all of you? Okay. So if you go for first order linear differential equation. So how you started your solution? Take the constant coefficient. Any differential equation. Then you will get the solution in terms of e power x. Yeah. You take any second order ordinary differential equation with constant coefficient. Simply go plus y is equal to 0. Then what the then y is the all the right? Okay. So if you take the suppose the coefficient of x square x y prime plus y. Yeah. Then what is the solution? You get solutions in terms of x power. Either x power n or x power, and they are exponential solutions to power. That is, there are two laws in physics and mathematics: the exponential law or the power law. The reason is any different equation you take, you must get solution in terms of or x power. So there are two exponential law or the power law solution, right? So which are most popular in physics also. Or you go for any relativity, you will get power law solution. Okay, so either you have to power law solution or exponential law solution, or you take the equation of state parameter, right? Okay, so basically, okay, to get this from equation 9, to get Einstein, so you need to go for right, go for determinant, right? Then you have to calculate the symbols. Okay, the transportation, because you have to go for the transportation. Then after the for the right. Okay, so you have to go for the rigid tensor. Then there is the scalar. Then you can come to the Einstein tensor. Is it fine? So that is what you can. This is the hands-on session. You can use the math tensor. Go for mathematical. There is a math tensor. You can use it and directly you can get all the values. Okay. Then you go for the Einstein tensor. Right. Similarly, I go for the momentum tensor. So the energy momentum tensor, as I mentioned, take the matter content of perfect fluid. So you have the pressure and the tangential pressure, right? And rho is the density. So this is the equation for the energy momentum tensor. Where this is, so these are the four velocity vector, right? Okay. Then coming to the diagonal graph, so we from this. Once you substitute values of the metric tensor and the four velocity, then you will get this energy momentum tensor in this form. So only you get the diagonal where the time coordinate is positive and all these special coordinates are negative. Okay, right. Then you get the now coming to the to go for the calculation. Now as I mentioned, so we need to go for the these three. Fine. So what we did, I think it. 1 minute. Yeah. Power law form. As I told, x power m is a solution or e power mx is a solution. So I assume this solution is a power law form. Is it fine? And I'm going to manipulate actually. So what I did here. Okay. So we have three minimum conditions for the shape function. The throat condition, flaring out condition, and asymptotically flatness condition. So the first figure is for the throat condition. You can see all of them. So at this point, your B of R is equal to R naught. Right? So if you go for the shape function or the radial coordinate, it is 0.9. So that's why I mentioned that your is not from 0. It will start from the throat radius. So here, so R starts from 0 to infinity. Because this point is the throat condition. Similarly, here B R minus R, so B prime R is here. Okay, so this is B prime R. So all these three conditions we have verified through the figure. Then the next question is how I choose the value of n. Why I have taken the values of n are this. Right? What is the reason behind it? Because I have only one arbitrary constant. So the model parameter, what I used to say the model parameter. So I have only one model parameter n. So how we got the value of n as 0.2, 0.3 and 0.4. Okay. So this is basically the code for the shape function, particularly the code for images. Okay. So these are the mathematical code to plot these three images. Right. Now coming to the, this is for the VR. That is BR minus R, and this is BR by R, and another is B prime L. Okay, so these are the mathematical. Right. Then last one is to all these four plots. Okay, now next question is the energy condition. As I mentioned, how we have chosen the value of M. So coming to the energy condition, the non-energy condition is rho plus PR with the radial bond. So now my intention is I need exotic matter so that the wormhole throat will open and will travel. Right? So the non-energy condition is rho plus PR. This is the value and it has to less than 0. Because the violation of non-energy condition is the indication of presence of exotic matter. So my intention is I violate the non-energy condition. So when this is less, so when L is less than 1, then obviously this is always less than 0. So that's why you have chosen N is 0.1, 0.2 and something. So any value less than 1, then your non-energy condition will violate and you can go for the other conditions. Is it clear now? Okay. So now I will show the images of the energy conditions. So these are the mathematical codes. Okay. So for the null energy condition, and this is the MD diagram for this toy model. Okay, dz by dr is root on r by r minus dr minus 1, and the code is here. I kept the code also. So this is the diagram code for the one. Okay. So now you can go for any model and go for the energy condition, then find out the value and check that whether your null and are satisfied. So this is a toy model where we wait for the energy condition. Okay. And then we plotted our MD diagram. Fine. Okay. Now come to the result status. Right. So what is the research currently we are doing actually? So the biggest puzzle again, whether it is science or science fiction. Right. Then the next question is how we will prove it. And is it possible that the exotic matter is the only way to describe the wormholes, or there is any other way? Right. So if researchers will succeed, then we can say that the time travel is possible, which is a question for the new generation. Fine. So you need to prove it. Then the time travel is possible. Okay. Right. Now coming to the modified theories of gravity. Particularly, I worked on modified theories of gravity. If you go for all my work, all are in modified theories of gravity. Rarely I worked in GR. Okay. So that's why I focused more on the modified theories of gravity. So the exotic matter here, right? To go for the wormhole, you need the exotic matter, which is the violation of null energy condition in general theory of relativity. Then the question is it required in modified gravity? So that is what my research starts. Fine. And my first article on wormhole is in 2017 in PRD, where we proved that exotic matter is not required. Yeah. So my first article on wormhole is in PRD, there matter is not required. Okay. So without the exotic matter, we can go for modified theories of gravity. Fine. So this article is in 2018. That is the second article actually. First article. So here we go. So Moria is my collaborator from Brazil, and Parvati is my first PhD scholar. So they will have to change because you know these Starobinsky models. Okay, these Starobinsky models are the is very famous due to the R square gravity. Right. So we have taken a modified gravity called the F of RT gravity. It is a coupled gravity where R is the Ricci scalar and T is the trace of the energy momentum tensor. Fine. So in this gravity, we proved that the exotic matter is not required. So what we did, we have considered the coupling. Okay. So R plus alpha square plus lambda T. So then we took the shape function in the power law form. And coming to the field equation, here the parameter is beta and A. So beta lies between 1 and A is this. Then we got the throat radius is 0.9. And here we validated the NS. The null energy condition validated, whereas the three minimum requirements, the throat condition, flaring out condition, and asymptotically flatness condition satisfies. Okay. So we replace the exotic matter. In the articles, we replace the exotic matter, right? Then we work with Kashmiri wormholes. So in Kashmiri wormholes, we go for the negative density, right? So the generalized uncertainty principle was used in this article. Being a mathematician, we use the generalized uncertainty principle, and we consider the Kashmiri wormholes in a modified FQ gravity. So this was done by Dinath and Sainthal. These are the two research scholars which work with me. And this Srihari Rao from JNTU. He worked at JNTU, now retired. So this is again the story will start. So it is basically go for the geometric trinity. There is an article by Lavinia Heisenberg. You can get the review article, geometric trinity of gravity. So geometric came from Euclidean to became Riemannian. Is only the Riemannian can explain the gravity? Because in Riemannian geometry, what you are doing? You are going with the affine connection, the Christopher symbol. Then the connection three terms after that. The affine connection has three terms: the contortion and the torsion. One term is the Christopher symbol. The other two terms in the affine connection are the contortion and the torsion. Right? Then you have other geometry. It is basically our Q. It is the symmetric teleparallel gravity. Then the torsion-based geometry is known as the teleparallel gravity. So, like R, particularly F of R gravity, which is completely based on Riemannian geometry, and they are Christopher symbol based. So, if you go for, as I mentioned, it has three terms: the Christopher symbol, then contortion, and the torsion. So, then from torsion, you will get the teleparallel gravity, and from the contortion, you will get the symmetric teleparallel gravity. So, then symmetric teleparallel gravity. So, the geometry is classified into three parts. That's why there is an article known as geometric trinity. There is a review article. So, in that article, you can get all the three types of geometry. Okay. So, one is published in the European gravitation between the European gravitation. Right. So, coming to the symmetric teleparallel gravity, the Q gravity. So, we have taken Kashmir effect. So here what we did, we placed the Kashmir effect in the wormhole throat. So we took three dimensions here and go on the parallel plate, parallel cylinder, and two spheres. Okay. So this actually can go for this one. 2209-2704. You apply it, then you can get that attitude. Okay. So in this attitude, we have taken this parallel plate, sphere. And the LEC is violated in this case. Okay. Then come to the latest one. So here simulation. So most of the guys nowadays using. So we did the ray tracing actually for the exotic tidal wormholes. So what we did here, we used the exotic tidal wormholes using the ray tracing. Okay. And here we did a simulation and we published in Astronomy and Astrophysics in 2022. Now the question is, if you can, because both the sides are the black holes. That's what we mentioned. Coming to the black hole geometry. Okay, so going for the observational data sets, we use the observational data set. And if you can connect these two, then you go for the wormhole. Is what you need to search. Okay, so the latest one is, as I mentioned, within next 10 years. Okay, so initially I told within next 10 years, like the image of the black hole, we can get the image of the wormhole. That is what already started. Okay, because everybody is talking about the quantum computer now, and India is also on quantum mission, right? So this is the same story started in November 2020. Okay, so a group of physicists has already created a wormhole. Okay, using quantum computer. They use the quantum computer and created the holographic wormholes. And this group working so hard and they are trying to capture the image of the wormhole in next 10 years. So that is what the present status of the wormholes. Okay, like as I mentioned before 2019 April 10, black hole is a mystery. So in future this will not a mystery, because when there is a theory, there is experiment. Never theories are derived from the experiment, but all the experiments are based on the theory, right? So since there is a theory, we hope one day the experiment will come and will capture. The outline what we discussed is and cosmology, because the most present research is the H0 and sigma tension, because the all the cosmologists are in tension whether it is correct or not, because there is a high sigma deviation. If you go for the Planck observation and Sue's observation, Planck observation says that it is 67 point something, and Sue's observation is telling 72 point something, near to 73. So 67 to 72, there is a high sigma deviation. In between, there are so many bingo, you go for CMB, there are so many observations are there. So all are in between 67 to 72. So that is not tensor. Okay. So it's not tensor. Then the detection of dark energy and dark matter. Right? There are observations are going on. Then finding the exotic matter with the negative energy density. And the Einstein's problem from 1916, cosmological constant, inflation, horizon, and the toughness problem. Okay. So these are the open questions in my perspective. Thank you for. Yeah.
Image is a proper image.
Yeah.
Holographic image.
Actually, they started in the laboratory. They used the quantum, and with quantum bits, they generated the image. But as you mentioned, whether they are able to capture with telescope or that is a mystery. That part they have to do. They started in the lab. They did in the lab. They generated the work from quantum bits. Now the question is, during that, using that theory, whether they can go for capturing the image or not. That we need to see. Yes. Yeah, we need it under. Yeah. That that depends actually. How much, see, where this science reached now. The question is, when you go, see, I'll tell another story. Okay. So how many Patani Samant? Samant Chandrasekhar. Because I know my research from their back of the right. So if you see Samantha, he Samantha, okay, with two bamboo sticks, he used bamboo sticks, and with two bamboo sticks he measured the distance. Particularly moon distance, he measured with bamboo sticks. It is 1917 and all. So it's 17th century. So that is telescope, right? And if you go for this astrology, all the astrologers the calendar, which you are getting the calendars and all, they are all astrologers. And if that is number six, and that is true. If that is correct, this number six and coming to the telescope. The science is developed in for such a way. We don't know. The like the present, once the AI came, how many jobs are huh? If you go for the next even opportunity, you can go for the next. Okay, so after that, this 7 week, we can go on with the but whatever the way machine learning and AI is coming, how many jobs right? So that is now open with platform, Google Gemini, I need this. Job, I need this. I need a lot of things for answer. Right? Now, it's 50% talking about middle. Scientific report, which is a nature journal. You give the reviewers, they are giving the report and they are submitting. So the presentation, even if I show articles, I know the students, they are I square, but they are in the articles. Because ChatGPT, you give ChatGPT, then That's what I'm telling. So then I yeah, yeah.
They have taken the Christopher symbol. Is that
Very
history? Take going
actually, we have to see, we can Google it. Okay, so the the because and then okay, so if you if you from zero, then it will go to if you the return then and so
the dominance of Christopher symbol.
now we have today. What is the so if you want to pause the video, right? And the go to the video. Close. Then you move to the video. And the video. So then this one there's contributing to meeting. Over so when in general in one more so they give give your that yeah, yeah, The second go on. Go on. Basically, I believe you take traffic and food. Again, so if two black holes can merge, right? One can travel from one into other. That is the idea. Is so you have 2 points. That is that one
You mentioned like 10 years ago. So, even the telescope knew where it was central. Everyone,
yeah. See, what see, what you no, that all of it. Yes. Repeat again. In dark matter, see, modify the magnetic law. We have seen there are programs Einstein theory of particularly Einstein law. We magnetic is completely different. Because exotic matter is based upon the non-energy condition. Your non-energy condition, how can you say that the foundation of condition is the presence of exotic matter. That's all. But that is different. In modified gravity, the non-energy condition satisfied, still there is one. Right? But vector is yes, the cobalt cobalt it is not there. The country not cobalt there. They are if you want so students yeah, these are the challenging thing. This is not yeah.
So there's a
Go on, go for it. Again, you go for the see the basic problem. You know, I am a teacher. So, one can but he can visit students. You go for a we don't have so that's why you got to enter or cut a 3 minutes later. It is very important. We can continue. Yeah.